We're now on section 14.3, relative strengths of acids and bases. Here we're going to assess the relative strengths of acids and bases according to their ionization constants, rationalize trends in acid-base strength in relation to molecular structure, and carry out equilibrium calculations for weak acid-base systems. So think way back to Chem 2A, Chapter 4, when we talked about some acids that are strong, something like HCl, HBr, this list you see here. They basically react completely with water and dissociate into their relative ions. For example, you take HCl, you throw it into water, and it becomes H plus or H3O plus and Cl minus. We also have strong bases. These tend to be hydroxides. You put them in water, and again, they're going to completely dissociate. You put LiOH, lithium hydroxide, into water, it becomes Li plus and OH minus. So Bronsted-Lowry acids, like we talked about in section 1, are proton donors. So the strength of an acid is measured by how much H3O plus it forms in water. So how many protons it's able to donate. If you have a strong acid, these basically give 100% H3O plus. But weak acids are going to yield way less than that. So these are some of the common strong acids and bases. There are not that many of them overall, especially compared to weak acids and bases. There's way more weak acids and weak bases. So if we are looking at some weak acids, we can figure out how strong it is by looking at its equilibrium constant, which we call the acid ionization constant, or Ka. If we were to write an equation for it, Ka, just like all of our equilibrium constants, we have products on top. So we have H3O plus times your conjugate base of your acid, your A minus. Good thing we don't do A minuses in the semester system. Divided by your concentration of your starting acid, your HA. So these concentrations are at equilibrium. Okay. The larger the Ka, the larger of H3O, the stronger the acid. If you have complete ionization, so that means that your amount of H3O is going to be very high, and your HA basically at equilibrium is 0. So for a strong acid, HA, for those of you in calculus, approaches 0. So then you have your Ka over H3O times A minus over 0. This approaches or becomes basically infinity. So strong acids essentially have a Ka of infinity. Very high Kas. So the larger the value of Ka of an acid, the stronger the acid. And then the opposite of that, the smaller the Ka, the weaker the acid. So here's some examples showing you some different weak acids and their Kas. Something else to kind of see here is the relative acid strength with charges. So if you have, for instance, you have the CH3CO2H in water, it has pretty low Ka, compared to HSO4 minus has a much higher Ka. So you can see these increasing, and you can just kind of also see and how that Ka gives you an idea of how well something can ionize in water. So HSO4 minus, even though it's still a weak acid, it is a stronger weak acid than that of CH3CO2H and HNO2. Another way we can measure the strength of an acid is with percent ionization. So this is, for an acid, percent ionization is equal to your concentration of hydronium at equilibrium divided by your initial concentration of acid. That should be a capital A, not a lowercase a, times 100. So here's an example looking at percent ionization. We want to calculate this for a 0.125 molar solution of nitrous acid with a pH of 2.09. So nitrous acid is HNO2. So our percent ionization is equal to our concentration of H3O plus divided by our concentration of acid. But we're not immediately given H3O plus, are we? We're given a pH. But that pH we can use to get H3O. Because pH, remember, is negative log of hydronium. And 10 to the negative pH is equal to our hydronium concentration. So that means we have 10 to the negative 2.09. And with that, we get 0.0081 molar. So now we have our H3O concentration, and we were given our starting acid concentration. So our percent ionization now is 0.0081 divided by 0.125 times 100. And we get 6.5%. Don't forget that times 100. So remember with bases, Bronsted-Lowry bases are hydrogen acceptors or proton acceptors. And a base, the strength of a base is measured by the extent to which it forms hydroxide ions in water. Strong bases give us 100% OH minus. Weak bases give us a lot less than that. So we also do have a Kb, a base ionization constant, that the higher that is, the stronger the base. So similar to Ka, we can write a Kb equation. It's equal to our Hb, so where B means base, times OH minus. So that Hb plus is our conjugate acid, divided by our concentration of base. I didn't put them in here, but your book also does give you 3 different equations looking at changing KBs. Again, the higher the KB, the higher or stronger the base. So the larger the KB of the base, the stronger the base. The lower the KB, the weaker the base. Okay. And just like before with percent ionization for acids, we can do this for bases. So that's equal to the concentration of hydroxide at equilibrium divided by your starting base times 100. Same type of equation. So Ka and Kb are inversely related. The larger the Ka is, the smaller the Kb, and vice versa. If you were to take the Ka of your acid and multiply it times the Kb of its conjugate base, you get Kw. And just to kind of show you, let's look at general equation of HA aqueous plus H2O, H3O plus A minus. And like we saw before, it's Ka is equal to H3O plus times A minus over HA. And if we have a base, we have A minus plus H2O gives us OH minus plus HA. So its Kb is equal to HA times OH over A minus. And if we wanted to add up these two equations, what we see is we have HA on both sides that cancel out. The A minuses are on both sides and cancel out. And then we add everything up and we get 2H2O becomes H3O plus OH minus, which is the equation for the autoionization of water. And when we talk about equilibrium, We talked about how when you sum a reaction up, your overall K is equal to the product of your individual Ks. So if we do Ka times Kb, that means we get H3O plus times A minus over HA times HA times OH over A minus. And you can see the HA's cancel, the A minuses cancel, and we get H3O plus times OH minus, which is KW. So you can also use what we just talked about here, KW. Let's say you know Ka and you want Kb, you can solve for Kb using KW. Some other things to know is the extent to which an acid donates a proton to water depends on the strength of its conjugate base. So if its conjugate base, its A minus, is a strong base, then any proton that's donated to a water molecule is going to be recaptured by that A minus, by that base. So it sees that proton, it's going to take it right off again. So that means we're not going to have much hydronium in solution because you have all this base there taking it away. So because of that, our HA, this starting acid, is a weak acid. The stronger the base, the weaker the acid. The stronger the acid, the weaker its conjugate base. Okay, so if A minus is a weak base, then it's not going to be able to recapture all of these protons being donated to a water molecule. So we're going to have a high amount of hydronium, making HA a strong acid. Strong acid, weak conjugate base. Strong base, weak conjugate acid. So you can see this picture here showing you where the stronger acids are on the same side as the weaker bases, weaker acids on the same side as the stronger bases. So they're opposite strengths. This is going back to showing those acids and bases we looked at before. And you can see their conjugate pairs are right next to each other. So perchloric acid is an extremely strong acid. Its conjugate base, perchlorate ion, is a super, super weak base. So it doesn't accept protons very much, if at all. Methane is a super, super weak acid, but methide ion is a very, very strong conjugate base. So, but why do these strong acids vary in strength? If you look at this, showing the increasing strength, everything above hydronium is a strong acid, but it's showing that they have a difference in strength. And everything below hydroxide is a strong base. Why do they value or change in their strengths if they're all strong? So the only acid species that's present in water is hydronium. So our strong acids, no matter what, you put them in water, they're all going to completely dissociate and give you hydronium. So this limit on the acid strength of solutes in a solution we call the leveling effect. So the way that we look at the strength of these strong bases, be able to say, oh, perchloric acid is the strongest, is by taking your acid and dissolving it in a solid that's less basic than water. So it's less basic than water. These acids end up becoming kind of weak acids, if you will, and they're going to have a difference in ionizations. And so then you can look at that difference in ionization and say, okay, so I put them in ethanol, for instance. And oh, look, this one ionizes more in ethanol than something else. So for instance, the binary hydrogen halides, HCl, HBr, and HI, they actually increase in strength going from top to bottom. So HI, hydrogen iodide, or hydroiodic acid, is the strongest of the three, followed by HBr and then HCl. So these are strong acids in water, but weak acids in ethanol, but still HI ends up being the strongest weak acid in ethanol. Now the conjugates of weak acids and weak bases are weak bases and weak acids respectively. And these guys are going to compete with water. So if you have solutions of weak acids and weak bases, you end up with an equilibrium mixture of reactants and products. So, but no matter what, keep in mind that when you multiply your Ka of your acid and your Kb of the base, you get Kw. So let's go ahead and look at an example because I've just been saying a bunch of letters and I know like it's confusing after a while. We want to use the Kb for the nitrite ion to calculate the Ka for its conjugate acid. So earlier in the section, we were told that Kb, and this is also a value you can look up. It should be in the appendix of your book as well as the internet. So Kb is given as 2.17 times 10 to the negative 11th power. So then its conjugate acid of NO2 minus, the conjugate acid, we're going to add just one hydrogen to it. So that means it's going to be HNO minus. I'm sorry, I wrote that wrong. NO2, NO2. Sorry, I wrote this wrong. It's NO2 and a minus. There we go. Copy paste decided to be weird. Okay. So we know that Kb times Ka is equal to Kw. So Kw or Ka is equal to Kw over Kb. And Kw is 1.0 times 10 to the negative 14th. Divide that by Kb, which we looked up as 2.17 times 10 to the negative 11th, and you get 4.6 times 10 to the negative 4. And you could then take this value, look in Appendix H. So Appendix H has values of Ka for different substances. You could look it up and go, oh, look, HNO2 has a Ka of about 4.6 times 10 to the negative 4. Awesome. There are other ways to determine Ka or Kb for a weak acid or base. You can always measure the pH of a solution, and you prepare it by dissolving a known amount of the weak acid or base. So you know your amount of weak acid or base you're dissolving, and you measure the pH. So you're given now pH, given some information to find the initial concentration of the acid or base, and then you can use that to find Ka or Kb. You can also get the pH similarly by using, calculating equilibrium concentrations or pressures. So you're given Ka or Kb, you're given some information that can be used to find the initial concentration of the acid or base. You can use that to calculate hydronium or hydroxide at equilibrium, aka use ice tables, and then use that to calculate pH. This is just showing some pH papers using that universal indicator. Here's another one. Okay, so let's look at an example. We're told acetic acid is the principal ingredient in vinegar. So when we eventually get to be in person and have labs in person, one day you'll work with glacial acetic acid, which is basically concentrated acetic acid, and it smells like you stuck your head inside a vinegar container, and it is concentrated vinegar. Actually, kind of an interesting thing in Germany, or I've gotten it at some German stores or certain delis, they actually have concentrated vinegar, and they're like, don't use it full strength because it has some pucker power. So it's it's more concentrated acetic acid. But that is what gives vinegar its sour taste. So at equilibrium, a solution contains 0.0787 molar, and the concentration of hydronium is equal to CH3CO2 minus, which is 0.00118 molar, and we want to know the value of Ka for acetic acid. So we first need to get the reaction for this, and if you aren't sure what the reaction is, you could always look up acetic acid in water. But the reaction is CH3CO2H, which you could figure that out as the formula by taking the conjugate acid of this base it gives us here, plus H2O, and then we get H3O, and our base CH3CO2 minus aqueous. So looking at that, our Ka is equal to H3O plus times CH3CO2 minus divided by CH3CO2H. And we were given all of these concentrations. We're told hydronium and CH3CO2 are equal, so those are 0.00118 times 0.00118 divide that by our acid, which we were told is 0.0787. And so that gives us a Ka of 1.77 times 10 to the negative 5th power. And here's a good old vinegar label. These tend to be reduced to 5% acidity. Any more than that, and it's, yeah. I love vinegar though. All right, let's look at another example. A little more, we're going to start looking at some more challenging ones. We're told caffeine is a weak base, and we want to know the value of Kb for it in a solution at equilibrium, given these equilibrium concentrations. So the nice thing about this is, again, it gives us everything we need to know. So Kb is going to be equal to our conjugate base, C8, or conjugate acid, sorry, H10, and 4O2H plus, times OH minus. Those are our product side, divided by our starting base, which was caffeine, C8, H10, and 4O2. And we were given our concentration, so we were told the acid concentration is 5.0 times 10 to the negative third times OH of 2.5 times 10 to the negative third over base, which at equilibrium is 0.050. So then put that all into our calculator, we get 2.5 times 10 to the negative 4th power for Kb. So for instance, my mom has really bad acid reflux, and if she drinks coffee or pretty much anything with caffeine, she tends to get a lot of stomach acid and has to take like Tums or something to try to wear it down. And she always says something like, oh, caffeine is acidic. In reality, caffeine is basic, but it's going to have that acid-base reaction going on. All right, so let's look at one a little bit tougher. We're told the pH of a 0.0516 molar solution of nitrous acid is 2.34, and we want its Ka, and we are given the reaction here. So this solution of nitrous acid does not account for equilibria. This is our starting HA concentration, if you will. So this is an initial concentration. Okay. So we don't know what our equilibrium concentrations necessarily are. So let's go ahead and start by making an ice table here. Remember, water is not going to be part of it because it is a pure liquid. So our starting concentration is the 0.0516. And we're going to approximate H3O as being 0 because it's not technically 0 because remember, H3O in pure water is equal to 1 times 10 to the negative 7th, but that's so low, it's going to be much less than our reaction. So we can just approximate that to 0. And we can go ahead and say that our NO2 starting concentration is 0. So it's 0 when we first start things. Now we can figure out, though, what our concentration of hydronium is once we've hit equilibrium because we're given a pH. So we know that 10 to the negative pH gives us H3O+. So then we have 10 to the negative 2.34. So H3O plus then is equal to 0.0046 molar. So now we know how much H3O we have, or that we've gained. So that's our change, plus 0.0046. Using our stoichiometry, same amount for NO2, 0.0046. And that means that HNO2 is losing 0.0046. Okay, it's all 1 to 1. So our equilibrium concentrations then of HNO2, 0.0516 minus 0.0046. This is 0.0470. For hydronium, it's 0.0046, and for NO2, it's 0.0046. So then our Ka for this reaction is equal to hydronium times the conjugate base, NO2, divided by HNO2. So that means that we have our H3O, which is 0.0046 times NO2, 0.0046, divided by our acid at equilibrium, 0.0470. And so we get a Ka of 4.6 times 10 to the negative 4. Now, one thing to not be confused about here is you are not using the 0.0516 as your concentration of HNO2. That is your initial concentration. You would use that if you wanted percent ionization. So your percent ionization then, remember, that's equal to H3O at equilibrium over your acid initially. So that would be at 0.0046 divided by 0.0470. So let's pop times 100. So let's grab the calculator. 0.0046 divided by, oops, not 470, sorry, 0.0516. 0.0516 times 100, we get a percent ionization of 8.91%. So that would be where you would use that initial acid concentration. All right. Do another example. Formic acid is the one irritant that causes the body's reaction to some ant bites and stings. So I've been bitten by a red ant before. It hurts. And we wanted the concentration of hydronium ion and the pH of a 0.534 molar solution of formic acid. And then we're given the reaction as well and a Ka value. So we're not told our equilibrium concentration, so we need to go ahead and do an ice table. As usual, water doesn't count because it's a liquid. We're starting with 0.534 molar of HCO2H, approximately 0 hydronium, and 0 HCO2. Now, we don't know the pH here, so we can't do like we did in the last example, but we know then that we're gaining some X amount of our products and losing some X of our reactant. So at equilibrium then of our formic acid, we have 0.534 minus X, and of our products, we just have X and X. So our Ka is equal then to products, so we have X times X over 0.534 minus X. And the fact that we have this very small Ka is at a magnitude of 10 to the negative fourth, that's not going to affect our large starting concentration. So we can go ahead then and do that. 0.534 is much, much greater than X. So we can approximate that X on the bottom to 0. And simplify this to Ka equals X squared over 0.534. And Ka is equal to 1.8 times 10 to the negative fourth. And so once you solve for both sides, get rid of the 0.534, take the square root, you get that X is equal to 9.8 times 10 to the negative third molar. That's an awful looking 3. Let's fix that. There. So if you wanted to check the assumption that X is super small compared to a 5.34, you could you have your X over 0.534, and that's equal to 9.8 times 10 to the negative third over 0.534, and that's 1.8 times 10 to the negative 2. So that is literally 1.8% of 0.534. So yeah, it's super, super small. And so then if you were to look at the ice table, so next thing that we have to do, oops. So now we need to figure out our pH. So when we look at our ice table, X is equal to our concentration of hydronium. So then our pH is equal to the negative log of 9.8 times 10 to the negative third. And so that gives you a pH of 2.01. So this is acidic also. Lots of examples in this section. So there's an ant biting someone. I don't know if you could pay me enough to actually do that. Okay. Next example, calculated equilibrium concentrations in a weak base solution. We want the concentration and pOH and the pH of a 0.25 molar solution of trimethylamine, which is a weak base. And we're given the reaction equation there and the Kb. So let's go ahead and set up our ice table. I feel like Chem 2A is all about conversions, and Chem 2B so far is pretty much all ice tables, isn't it? So we're starting out with 0.25 molar of trimethylamine. We have 0 of the conjugate base, and we're going to go ahead and use OH minus approximation to be 0, just like we did with hydronium, because it's 1.0 times 10 to the negative 7th power in pure water, so it's too small to really affect anything that's happening here. So we're losing some X amount of trimethylamine and gaining some X amount of our products. So at equilibrium, we have 0.25 minus X, X, and X. So then we have our Kb, so equal to products over reactants. So we have X times X over 0.25 minus X. And we can go ahead and assume that X is much, much less than 0.25 because of how small that Kb is. So then we get that Kb is equal to X squared over 0.25. And Kb is 6.3 times 10 to the negative 5th power. So then getting X squared by itself, taking the square root, you get that X, which is equal to our concentration of OH minus, when we look at the table, is equal to 4.0 times 10 to the negative third molar. So there's our first thing we wanted, the concentration of hydroxide. So then pOH is equal to the negative log of OH, which the negative log of 4.0 times 10 to the negative third. So pOH then is equal to 2.40. And pH is equal to 14 minus pOH. So that's 14 minus 2.4. And we get a pH then of 11.60. So this is a pretty basic solution. All right, so now here's a much tougher example. This one we cannot use simplifying assumptions. So sodium bisulfate, NaHSO4. I don't know how that typed like that. NaHSO4, there we go, is used in some household cleaners as a source of HSO4 minus ion, a weak acid. What is the pH of a 0.50 molar solution of HSO4 minus? All right, and we're given the reaction and our Ka. Notice this Ka is only 10 to the negative 2, so this is actually a pretty big Ka. Okay, goes away. Ice table is ready for us. So we're starting with 0.50 molar HSO4, losing some X, 0.50 minus X, starting with about 0 hydronium, 0 sulfate, plus X, X. So Ka, this value we're given, is equal to x times x from our products divided by our reactant, 0.50 minus x. So this Ka is if we were to make this into a standard, so it's 0.012. Notice we have that 0.1, yeah, that coincides with that 0.5. So it's too big to be able to say that 0.50 is much greater than x. We cannot do that. So you would, if you did, you would get that x is 0.077 molar, and that is not significantly less than 0.50. So we need to solve this using quadratics. Okay, so then we have that Ka times 0.50 minus Kax is equal to x squared. So then we get that x squared plus Ka times x minus Ka times 0.50 equals 0. And just substituting in Ka and doing our math, then that gives us x squared plus 1.2 times 10 to the negative second times x minus 1.2 times 10 to the negative second times 0.5 is equal to 6.0 times 10 to the negative third. That's equal to 0. So we've got a good old-fashioned quadratic. There are such things as quadratic equation solvers. So if you go online, put like quadratic equation solver, you can type in what your A, your B, and your C is, and it'll spit out your answers for you. Just make sure that, you know, if you have like this minus 6.0, that you have that your C is equal to negative 6.0 times 10 to the negative third. But when you do that, the negative root can be discarded, but you get that X then is equal to our hydronium concentration when you look at the ICE table, which is then 0.072 molar. So then the pH of our solution is equal to the negative log of that, which is equal to 1.14. So as you're seeing with these weak acids and bases, some are stronger than others. Again, Bronsted-Lowry acids are proton donors. If we were to look at the binary compounds of hydrogen, so HA, so maybe HCl, HF, HI, the strength of the acid depends on how easily the bond between the hydrogen and the nonmetal is broken. Another example would be, H2O, H2S. These are still hydrogen with one other type of atom. The acid strength itself is going to increase as its bond strength decreases, because we want to be able to give the H away. So if it's holding on to that H pretty strongly, it's going to be more of a weak acid because it doesn't want to give it away. So this is a periodic property in terms of your nonmetal. So A represents your nonmetal. When you're going down a group, you're going from top to bottom, your acid strength increases. When you have orbitals that are similar size, these are going to form very strong bonds, and you're getting good orbital overlap. So think back to quantum. When you have orbitals of different size, you make weak bonds because you have poor orbital overlap. Hydrogen is the smallest element. So then you have atoms are getting bigger as you go down the periodic table. So that's going to then weaken that hydrogen atom bond, because the atoms are getting bigger and bigger going down a group, making it a stronger acid because it can give away that hydrogen a lot easier. This is why HF, hydrofluoric acid, is actually a weak acid. Even though it's a binary acid and it's a halogen, the bond between the fluorine and hydrogen is so strong, fluorine doesn't want to give it up. Going from left to right on the periodic table, our acid strength is increasing because we're making a more polar bond. So more polar bond, that H plus can come off easier because it's more charged. So electronegativity is increasing across a period. So that hydrogen atom bond is becoming more and more polar as our atom is changing. And this bond is weakening going across the period, making our acid strength go up. So here's just kind of zooming in on 2 periods in the periodic table. You can see the Ka's changing as you go from left to right and top to bottom, and showing you how things are, the acid strength is increasing going left to right, top to bottom, and our base strength then doing the opposite, increasing going right to left and bottom to top. We also have ternary acids and bases. So we talked about binary, that's just hydrogen and one other atom. Now we have ternary. So ternary compounds have hydrogen, oxygen, and some other element, some E. So E means element. These can be basic, acidic, amphiprotic. It all depends on the electronegativity of your element. And notice I'm saying element here. This could be a metal, it could be a nonmetal. If your electronegativity of your element is low, then you have this polar bond or an ionic bond and bond A, so which is your element and oxygen. So if your element is, say, sodium, then the bond to oxygen, it's going to have, sodium has a low electronegativity, so it has an ionic bond with oxygen. So that means that it has a very, very strong bond to the oxygen, but that when you go in water, that they might be able to split apart into their separate ions. So this makes a base because it readily releases OH minus. The metals, again, have low electronegativity. So metal hydroxides tend to be bases. If you have a high electronegativity of your element, then you have a covalent bond in bond A. So then the electrons in bond B, which is between the oxygen and hydrogen, are being pulled closer to your element. And this bond B is polar, but it's weak. The oxygen-hydrogen bond ends up being kind of weak in these compounds, so H plus can pop off a lot easier, making this an acidic compound. So these tend to be nonmetals that are the element because they have high electronegativities. Another thing to see is that as the oxidation number of your central atom increases, so does the acidity. So looking at nitrous versus nitric acid, nitrogen in nitrous acid has an oxidation number of +3, whereas in nitric it's +5. So it's a much stronger acid. So that means that this hydrogen from the nitric acid can come off a lot easier due to that electronegativity. Sulfurous acid, sulfur has a +4, whereas sulfuric it's +6. So that hydrogen, again, can come off a lot easier. It's a much stronger acid. If you have some intermediate E, then you're going to have usually an amphiprotic molecule. So it can be an acid or a base depending on things. So water, for instance, is HOH. So that E is hydrogen. In the presence of a strong acid, it's going to act as a base. In the presence of a strong base, it's going to act as an acid. Now, metalloids are interesting. Metalloids and elements near the metalloids have these intermediate electronegativities. For example, aluminum, oh gosh, how do I say it? This is hydrated aluminum hydroxide. When you put it with base, then it forms water. And an interesting complex here. LH2O, 2OH4. Oh, that is minus sign. And this ion that it's converted to by adding base actually makes it soluble, so now it dissolves in water. Now it's basic water. I don't know if you can hear him, but Dexter is currently yelling at me. What? Okay. Now, if you add some acid to it, so we're actually adding 3H2O. then we get Al H2O6 3 plus. Dexter, can you not headbutt me while I'm trying to write? Aqueous plus 3 waters. Excuse me, can you get off my book, please? Thank you. So then when you're adding that acid, you're also making it the aluminum complex soluble in water. So both of those, it's going to dissolve it in water, but it's forming different